Okay, today is the last lesson in this unit. Now, for the trigonometric identities, what you're going to be responsible for after you've practiced doing some in class is it's going to be an assignment, and it will be an individual assignment, and everyone's assignment will be slightly different. Okay, so our goal today is I can prove trig identities. So, section 4.6 from your textbook. So, trigonometric identities. Okay, now, first of all, trig identities are equalities that are true for every single value of occurring variables. So, in other words, an equation that is always true regardless of the value of the variable. So, remember earlier when you did some work with the exact values worksheet and it asked you to show that one side equaled the other. Very similar to that. However, they expected you to put in um, one variable at a time. But what we want to do is we want to prove something so that it doesn't matter what variable we use, it is always true. So our goal is to use the most basic identities, which I'll talk about in a moment, and mathematical manipulation. Now that manipulation might be common denominators, it might be factoring, it might be dividing, multiplying, adding, subtracting. So everything that you normally would do to solve an equation. So we're going to use the basic identities and mathematical manipulation to, and what we're actually doing is you're actually going to prove other identities. Okay, so it's similar to a left side equals right side check, but the difference being is you're proving. So there's a few different things that are involved when we're actually proving something for every value. So first of all, let's talk about the basic identities that we have at our disposal, okay, before we actually talk about the proof. Now, these basic identities, you have to know these. Okay, so these are the ones, these are part of your tools. Mathematical manipulation, you've been doing that for quite some time throughout high school. However, these basic identities are your other tool. So the Pythagorean identity is is sine squared theta plus cos squared theta equals 1. And the way that we got that identity had to do with the unit circle. And remember, we drew a triangle, and we knew that sine was the same as y. So y squared plus cos is x squared equals 1. And that was based on that unit circle with uh, sorry, I can't seem to talk and draw today, with radius of 1, okay? And we discovered that we have an x value and a y value. Now, using Pythagorean theorem, that's where we get 1 squared equals the x squared plus the y squared. And because we know x and y stand for cos and sine, that's where the Pythagorean identity comes from. Now, the Pythagorean identity can be rearranged and it's still the Pythagorean identity. So sometimes it's useful for us to have it rearranged in such a way that I have sine squared theta. So just by manipulating, by subtracting cos squared from both sides, we end up with sine squared theta equals 1 minus cos squared theta, and conversely, cos squared theta equals 1 minus sine squared theta. Now, to be honest with you, I just remember this one and I can easily manipulate these ones. But I'm always looking for this kind of pattern in my proofs. The next identity, and we've talked about that too, is tan. Tan theta equals sine theta over cos theta. Now, that is true. We've talked about that before, that it's y over x. Again, using the unit circle. And I just want to get my pen up here. Lovely little thing. That was sarcastic, by the way. All right. Now, what I can do, this is also the quotient identity. So if I take and square both sides, so tan squared theta equals sine squared theta over cos squared theta. So that is still the quotient identity. Okay. Then what we have is our reciprocal identities. Okay. And those include cosecant theta is 1 over sine, secant is 1 over cos, and cotangent is 1 over tan theta. Okay, so let's see, what are we expected to do with these basic identities? Okay, first of all, format of the proof. First, we only work with one side, and it looks like I've missed something, but I haven't. It's one side at a time. So you're not going to flip back and forth between left side, right side. Okay, you stay on one side and you want to manipulate it so that you get to the other side. Okay, you complete one mathematical manipulation per line. So you maybe see that both sides are equal, but you can only do one mathematical manipulation at a time. So you can't divide and add at the same time. So you do one, then you do the other. It's important that you indicate what side you're working with, okay? So if you're with the left side, make sure that I know that you're with the left side. If you're with your right, the same thing. So there's no guesswork. Okay, the next thing is to state to the right of your work what mathematical principle allows you to do the step that you're doing. So mathematical principle. So it might be common denominator. It might be dividing by fractions. It might be factoring. So that's the mathematical principle that you would write down. Or it could be that you're substituting a Pythagorean identity for what you have. Okay, so that's the mathematical principle that you need to put. Now, short forms are acceptable. Okay, so example, if I'm finding a common denominator, it's fine if you put C denominator or something along that way so that we know exactly what you're doing. The next thing also to consider at all times is you use the basic trig identities as substitutions to get you to make the one side equal the other. And finally, after you get your left side equal to right side, or finished your proof, so in other words, you did show it, you use a therefore statement, and what you're doing is you're just repeating the identity you just proved. Okay, so in a sense, you're actually repeating the question if you want to look at it that way. Now, a few different hints here that come in handy, and of course, there's lots of them. One hint is choose, I always find that it's easier to choose the most complicated side because if it's most complicated or it looks the messiest side, it means I can do more mathematical manipulation to it. Also, remember finding common denominators is pretty much the norm here. Okay, so let's take a look now at a couple examples. Actually, I have more than a couple. Okay, so first of all, I have tan squared theta plus 1 equals secant squared theta. All right, so when I look at this, I have to decide what side do I think is the most complicated. Sometimes it's harder to determine, and it doesn't really matter which side you choose. However, as I said, usually the more complicated. Now, when I look at this one, I'm looking at tan squared theta plus 1. I'm thinking in my mind that that's more complicated than secant squared theta because yeah, I can probably start with that, but it would be a little bit harder for me to come up with a manipulation. This one I probably could. Okay, so that first step that we do is we actually draw get my pen up here. We actually draw kind of like a table, a T table kind of thing. And so I'm going to put, because I'm going to do left side first, I'm going to put left side here, and I'm going to put reason here. And I usually put a straight line down, and so I actually am going to make a straight line, and nothing wants to work today. There we go. Okay, so I usually set it up like that. You can actually make it like a T table if you so wish. All right, so the first thing that I notice is on that left side, I usually rewrite it down so that it's right there for me. And do as you're told. All right, so we have tan squared theta plus 1. Now, because I need to somehow get to secant, tan squared doesn't have secant in it. So I'm going to do a manipulation right away, a substitution, and I'm going to change it to the quotient using the quotient identity. So tan squared theta is the same as sine squared theta over cos squared theta. The reason I can do that is that's the quotient, and I usually just put ID to stand for identity. Now I have this. This to me looks like a fraction. So I'm going to find a common denominator with the 1. And so my common denominator then would be cos squared theta. So I have sine squared theta. So yes, there's a lot of writing down, even though I can see the end of where I want to go. A proof, I literally have to take the time and write out each step. So that would be cos squared theta over cos squared theta. And what did I do? I found a common denominator. And I'll just put CD, common denominator. So now I'm going to add those together. So I have sine squared theta plus cos squared theta all over cos squared theta. Okay, so what did I do? What did I did? I add, okay, and you can add fractions if you want to put that. Okay, so now when I look at this, remember I want to somehow, at least now I have a cos at the bottom. But my problem is, what do I do with the top? Well, the top, if I look back here, is actually the Pythagorean identity. So it's actually the Pythagorean identity. So I can just do a substitution again. So that's the same as 1 over cos squared theta. And why could I do that? Well, the reason I could do that, remember, is because that was the Pythagorean identity. So to the side, I'm going to put, we'll just use Pyth ID, so I don't have to write out Pythagorean. Now, in a formal proof, like if you're proving it for um, to be published, obviously you wouldn't use that many short forms. Now, if you notice, I have 1 over cos squared theta. Remember, I want secant squared theta. Well, there's a reciprocal function, so that is actually equal to secant squared theta. And the reason being, it's reciprocal ID. Now I have this equal to the right side, and I finish off my proof with therefore tan squared theta plus 1 equals secant squared theta. Okay, so it's kind of like a puzzle in a sense. Now, some people can see how the pieces go together, other people have a little bit more difficulty. So I'm going to stop this and we're going to do the next one, which is slightly different again. And I actually have, I believe, 5 examples. How many you watch is totally up to you. However, the first 3 or so I've seen before myself, and the last 2 I haven't. So I have to figure them out with you. And unfortunately, you're not there to help me.